continue from the previous section, started kind of interrupted by a phone call about this unsymmetric bending. And here, let us take a look at example and to see how can we proceed. Okay, so this is unsymmetric bending, and on the cross section here, and the beam will be looking like, if you look into 3D, then the beam will be looking like this way. So on the cross section, this is apply the bending, and here is a double arrow sign here, and I ignore, and then if you like, you can have the double arrow, but sometimes I ignore it. So this is a double arrow. Okay. So M is here, the 600. You simply decompose into Y and vertical Y direction and horizontal Z direction here. So that means here the horizontal component MZ, and that component basically is M times cosine 30 degrees. So this is M and cosine 30 degrees, and cosine 30 degrees is square 3 over 2. Okay, so that is the 300 square 3. And my, this one is M times sine 30 degrees, and basically that one equal to M times 1/2, and that is 300. So that is 300 here. So now we decompose into this way, and then here again, this is the double arrow. So let me using the double arrow. Okay, so not to confuse people, and there's a double arrow here. And under this case, again, apply what we have learned from the pure bending, and here you should be able to clearly identify and two things. One is MZ is applied in this way. So here Z axis about which MZ double arrow sign applied, this is our neutral axis. Okay, and again, and here I will do the last demonstration here. So let me explain why. So here is our double arrow assigned here. So this is MZ. Okay, and so here let me label the coordinate systems. So this is Y, this is Z. The first things here, I want to show you how to identify, how to locate the neutral surface, neutral axis here. So let me put into three-dimensional drawing here. Okay, so right now the MZ applied to this, and now we apply our right hand rule. So you should know the bending is like this. Okay, the other side, the bending will be like this. So under this case, the bending is in the way the curve down this beam. So beam will be curved down, become like this. I try my best to show. Hopefully you see this one clearly. So basically that is to bend curve down respect to the Z axis. So under these situations, you should be able to clearly see this is our neutral surface. Here I try to highlight this is our neutral surface. Okay, in this case, this is the neutral surface. Again, if you still not clear why the neutral surface is like this, then you need to go back to the previous section from the very beginning of this chapter to see, to learn how the neutral surface be defined from there. Okay, start from there. This is a neutral surface. Intersection of the neutral surface to our cross section is the neutral axis. So here we therefore identify this is the neutral axis for this case, for this subsystem. Okay, now we move on to this another subsystem, this due to MY here. So this case, this is the neutral axis for this subsystem. Okay, and then the second thing is, once we identify the location of the neutral axis for individual subsystems, then the second thing is to identify which regions is in tension, the other region is in compression. For this case, you can see the upper portions basically will be stretched, and then in this case the upper portion will be in tension. And again, if here you still not clear why the upper portion is in tension, you need to go back to the very beginning, the starting sections of these chapters to learn from the beginning. Okay, and so here we identify this upper portion is in tension, the lower portion again is the shortened portion, the fiber in the shorter portion in the lower portion is shortened, so that is in compression here. Okay, in the similar way, and this will be the left side. The left side will be tension, this will be in compression. So with everything ready, then we can begin to calculate. And for this subsystem, and let me use the color, for this subsystem, the magnitude of the stress has magnitude equal to, again using our template, M is the moment being applied, so for this case is mz, and the second symbol is y. Y simply is the physical meaning is the distance from the point to the neutral axis. So here let me illustrate. For example, here we be interested in this point here, for example. Okay, so the second symbol here in our my over I, that kind of the equation here. This y indicating is a distance from the point to the neutral axis, and that one basically here you can see this distance simply measured per our coordinate system is y. Okay, so this distance is y. So that is the y here. Okay, and I is the moment of inertia with respect to the neutral axis. For this case, the neutral axis is z axis, so here is z. Okay, and now again we look for this subsystem. The sigma has a magnitude and equal to, again we're using our template here. So m is the moment we applied is my here, and again let me say look for this point here. So the second symbol physical meaning is the distance between the point to the neutral axis. So right now is this distance. This distance actually is our is the z coordinate of this point. Okay, so that point z here. Okay, so this is the point we're interested. The distance from here, basically you can see that it's measured by the z coordinate. Okay, and I is a moment of inertia with respect to the neutral axis, which is y axis. Okay, so with everything ready, we know the attribute and tension, compression, and we know the template for calculating magnitude. Then we can proceed. At point A, where is point A? Point A is here, the corner here. So this is a point A. This is a point A. So here the stress at point A will be equal to the superpositions. So this is superposition of the two subsystems. Now for the first system, the A at this point is tension because that's located in the tension, and the magnitude equal to mz and iz. And what is y? Y is the distance from A to here. So we'll look for the dimension, that's 0.75. Okay, now for this system here, A is located again in the tension region. The magnitude given is this template my. And what is z? Z is the distance from A to neutral axis, and that dimension is 0.25. Okay, and then I respect to y here. Okay, so that is the positive number you added up together. Then for sigma b, okay, sigma b, let me change the different color. How about that? Oops. So b is here. So let me label b is here and b is here. Okay, so sigma b. And again, in these subsystems, b has the magnitude like this. Okay, so nz and iz, and b is the, what is this one? The y is a coordinate, that is a distance from here to here. So that is 0.75 here. Okay, and B again is in tension region, and now we superpose, and B for the subsystem case, and again my and iy, and then B is a distance measured from that is a distance measured from here to here, and so here this number is 0.25 here. Okay, and then B is located in compression, so there's a compressor here. Good, so you should be able to proceed the point D there. And this page basically showing the detailed calculations for what I've just described here. The second questions here I want to describe, not answered, not asked by this example, but I want to propose is this. Let me erase the space for working. I want to let you know using this example to demonstrate how to determine the orientations of the neutral axis for this case. Okay, so let me erase the space here. In the meantime, you can begin to kind of think about and then probably proceed your calculation to see whether your thinking will be right, and after checking with my following the demonstrations here. So here I want to know is the determine or draw the neutral axis over the given cross section. Okay, I want you to draw the neutral axis over this cross section here. So again, and here the neutral axis by definition is where the stress equal to 0. Okay, and then the stress equal to 0, from here you can see we're going to superpose the stresses from the two subsystems, and to make up the 0 stress, and very likely it will happen in which quadrant? We'll look at here. Let me divide into 4 quadrants here. Okay, so 1, 2, and 3, and 4. In the first quadrant, and that is positive superposed to a negative, so that is a positive. Let me use a better color here, it's not very clear. Oops, let me erase this one. In the first quadrant is this, that is this region is positive value, this region is negative value. So in the first quadrant, that is the superpose of positive value superposed to a negative value here. In the third quadrant here, that is the negative value here, and superposed to here, that is the positive value here. Okay, so that is the 2 quadrants that very likely will have the superposition of the stress become 0. So we'll look for here. So the strategy is this. I simply say I pick a point, for example, say let me draw this one here. So out of space, let me put this one here. That's okay. So there's a y-axis, there's a z-axis. So here, and we identify the stress, the 0 stress will be happening in the first quadrant, third quadrant. So let me, how about this? I pick randomly a point E, and I ask the neutral axis passing through E. Okay, so for E, we know the distance. Let me label this one. That is the E's Z coordinate, and this distance is given by E's Y coordinate. Okay, so E right now is we simply is a superpositions of the from the two subsystems. We simply follow the same template. So for the first subsystem, that is MZ, and Y is the coordinate from E to now the system is in the neutral axis here, so that is a coordinate between the point to the neutral axis, and which is given by y coordinate here. We don't know the y yet, but here I just symbolized, and this is the IZ. In this quadrant, first quadrant, this is tensor, so for this one. Okay, now we superpose to the subsystem 2. Subsystem 2, we have the magnitude and again my. Again, this one has the E is point here, and that is the distance from the point to this neutral axis, which is the Z coordinate here. And again, we copy this one from here. In this subsystem, where the E locates in this subsystem is compressive, so that is here. We ask in this one equal to 0. Okay, and from here also we know that when Y and Z both 0, indicating the origin here, this will also equal to 0. So once we figure out the YZ, we simply linking the 2 points together. That will be orientation of the neutral axis. So from this case, we are given MZ equal to 300 square 3. We given MY equal to 300. We calculate the IZ and IY. And that is the moment of inertia with respect to y-axis or z-axis. So from this case, we should be able to solve for and y equal to 5.2 z. Okay, so y equal to 5.2 z. So that means here with this slope, and you can just label it. And so if you have this equation, you get the answer. And then if you want to draw it precisely, I can draw that one. And let me erase this notation here. Oops. How about this? Let me draw this one here. So that will be orientation something like this. Very steep. Okay, so this is the neutral axis. And then in terms of the slope, y equal to the slope equal to 5.2 here. Okay, that's based upon our result. So hopefully using this comprehensive example that help our previous, the part 1 illustrations.